In this video, we're going to prove the important fact that the determinant of AB is the determinant of A times the determinant of B. Assume A and B are both n by n matrices. And we're going to do this, in 3 cases. Case number 1. A is singular. Okay, so A singular implies that A reduced has a row of zeros. But that implies that the determinant of A is 0. So we know the determinant of A is 0. Now, AB will also have a row of zeros. So that implies that the determinant of AB is 0. Well, if the determinant of A is 0, that implies the determinant of A times the determinant of anything well-defined, and the determinant of B is well-defined, is equal to 0. So I have both of these equaling the same value. Therefore, the determinant of AB is equal to the determinant of A times the determinant B precisely when A is singular. So now that that case is done, we're 100% finished with the case when A is singular. The theorem follows. So case 2 will be A is non-singular. And what we're going to do is look only when A is an elementary matrix. A is non-singular. Let me even say it. And elementary matrix. And now we have 3 subcases. Type 1. A is the matrix that interchanges 2 rows. That interchanges 2 rows of the matrix that gets multiplied by B. That gets multiplied by A, which is B. Don't know why I was hiding the fact B. Okay. So now, the determinant of A times B. Now, remember, this is a matrix that interchange 2 rows of B. But we showed that that's not going to equal the determinant of B. It's going to equal to negative the determinant of B, which is the same as negative 1 times the determinant of B. Of course, if I show that A had determinant negative 1, we'll be okay. Now, the determinant of I is 1. Okay. The determinant of A times I, since A just interchanged 2 rows, is going to be negative 1. But A times I is A. So, the determinant of AB, which we know is -1 times the determinant of B, but another way of writing -1 is the determinant of A times the determinant of B. We got it for case 1. Case 1, done, kaput. Let's erase this. So let me just write it here. The determinant of AB is equal to the determinant of A times the determinant of B. Now, let's go on to case number 2, or type number 2. Type 2. A is the matrix that multiplies a row by K. Okay, that's what A does when multiplied by B. So what happens is AB, the determinant. Now AB is B, where one row got multiplied by K. Well, we know what the determinant of B is. It's the determinant of B. But if we multiply one row of B by K, we're going to get back K times B. K times the determinant of B. I just need to show that the determinant of A is K. Well, that matrix is the identity matrix. It is the identity matrix where on one diagonal the entry is K. On one diagonal, one entry on the diagonal is K. Now, this is clearly a diagonal matrix. So the determinant is the product of their elements on the diagonal. If you prefer, it's upper triangular because everything below the diagonal is 0. So the determinant is the product of the entries on the diagonal. It's lower triangular, however you want to think about it. This determinant is equal to 1 times 1, eventually times K, times 1, times 1, times 1. It's K. So, K, another way of writing K is the determinant of A times the determinant of B. But that's what I wanted to show. So, the determinant of AB is the determinant of A times the determinant of B. Okay. So type 2 worked. Now we go on to type 3. Type 3. A adds a multiple of one row to another row. To another row. Okay, so A times B, well, that's almost B. It's just B with a multiple of one row of B added to another row of B. That turns out to just be the determinant of B, which of course is 1 times the determinant of B. I just need to show that that 1 is A. I wrote it, but I didn't show it yet. Need to show that that's 1. Well, what type of a matrix is this? Well, it's always in the form of 1, it's always the identity matrix. It's always the identity matrix. It's always the identity matrix where one of the entries, one of the zeros, has been changed. Maybe it's 7. What this does is to row 2, first, second, third, it adds 7 times of row 3 to row 2. But, or maybe that 0 became a 10 down here, but not in both places. So either it's upper triangular or it's lower triangular. Either way, its determinant is our product of the entries along the diagonal, which is 1. That matrix is A, and the determinant of A is 1. So instead of 1, I put the determinant of A, and I have it. For all cases, when it comes to elementary matrices A, if A is elementary, we know that the determinant of AB is the determinant of A times the determinant of B, if A is elementary. If A is elementary, we got it. Now to the real case. So let's write this down. We know if A is elementary, then the determinant of AB is the determinant of A times the determinant of B. Star. Now, case 3. The general case. A is non-singular. A non-singular implies that there exists elementary matrix 1 and 2 and up to some number, say M, such that A is equal to EM minus 1, all the way down to E2, E1. That's what A equals. So now, the determinant of AB is equal to the determinant of EM minus 1, all the way down to E2 times E1 times B. But this is equal to the determinant of EM times EM minus 1, EM minus 2, all the way down to E2 times E1 times B. Now, this matrix is elementary, and a product of these matrices is a matrix. The determinant of an elementary matrix times another matrix, well, star comes into play. This is equal to the determinant of EM times the determinant of EM minus 1 times EM minus 2, all the way down to E2, E1 times B. But this is equal to the determinant of EM times, think of it as this matrix, elementary matrix, times that matrix. So this is the determinant of em minus 1 times the determinant of em minus 2 times em minus 3, all the way down to e2, e1 times b. So we have the determinant of em times the determinant of em minus 1 times this determinant. But that's this matrix, elementary matrix, times that. Invoke star. This is the determinant of em minus 2 times the determinant of the rest, em minus 3, all the way down to e2 times e1 times b. And we continue in this fashion, and at some point we get e to the m, e sub m, the determinant of em sub 1, all the way down to, say, e2 times e1b. So this is the determinant of em times that determinant times all of these determinants times the determinant of e2. Now since e1 is elementary, that star keeps coming into play. We get this. Okay, so we have b separate. Okay, it's isolated. So I have the determinant of AB is equal to this mess times the determinant of B. Somehow we have to show that that's the determinant of A. Okay, now we go in reverse order. We combine them. Since this matrix is elementary, the determinant of this matrix times the determinant of that matrix is the determinant of their product. Times the determinant of em minus 2 times em minus 3. Oh, okay. All the way down to the determinant of e2 times determinant of e1 times the determinant of b. Now, when you multiply, I just want to think about this for a moment. We know that the determinant of AB transplant, that's not going to work. Okay, so I went the wrong direction. I apologize. Big mess here. We only know that if the matrix on the left, this is the left one, if the determinant on the left is elementary, then the determinant of this elementary matrix times the determinant of that matrix is the determinant of the product. Okay, so I know that E2 is elementary. And when I multiply it by E1, I will get the determinant of E2 times E1. Let's not forget B. Let's not forget everything before it. Determinant of EM, the determinant of EM minus 2, ... Now here, we're going to have the determinant of E3. Now the determinant of E3 is elementary times this. So we're going to have up to here, we're going to have the determinant of EM times the determinant of EM minus 1 all the way down to the determinant of E4. Now the determinant of this elementary matrix times the determinant of that matrix is the determinant of the product. And let's not forget the B at the end. And likewise, I can put the 4 in there and the 5 in there. So continuing in this fashion, I get the determinant of EM times the determinant of EM minus 1, all the way down to E2 times E1 times the determinant of B. But we have it. This here is the determinant of A, because that's A. So the determinant of A is the determinant of A. This is A, and I have the determinant of it. So this is the determinant of A times the determinant of B. And we showed that the determinant of AB in the general case where A is non-singular is the determinant of A times the determinant of B. So case 3 was for any non-singular matrix. We got that. We got the results we wanted. And case 1, we also got this result where A was singular. So whether A is singular or non-singular, we show that the determinant of AB is equal to the determinant of A times the determinant of B. These proofs are quite doable. I didn't do anything advanced. Okay, nothing at all. If you like videos like this, please subscribe to my channel. Leave a comment. Most of all, watch and learn. See you folks in the next video.